Okay. So I think not something that's not normally covered in this class, although I did learn it when I took the counterpart to this 22 years ago. So we've seen a whole bunch of integral theorems for some one that you've known for a long time by now. Fundamental theorem of calculus, and then fundamental theorem of line integrals. Basically extends this to gradient, multivariable case. That if you have a conservative vector field that is integral over a curve, is just equal to the function f evaluated at the endpoints of the curve, just like we have the endpoints of the interval in this case. And then we have, bless you, Green's theorem, let's do it again. That the integral over a region in the plane of this expression is equal to this expression over the boundary curve. And then similar to that, for a non-flat surface, Stokes' theorem, integral over a surface, curl of a vector field is equal to the integral over the boundary curve, of the vector field itself. And then finally, divergence theorem deals with a solid. If the divergence of a vector field is the integral over its boundary surface of the vector field itself. Okay. What?
What?
Yeah. Anyhow, so what all of these have in common is an integral over a higher dimensional region is related to an integral over its boundary. We have expressions involving vector fields in all of these cases, and then we have derivatives of a components in the integral over the higher dimensional region. That's true even of a fundamental theorem of calculus. Now here we just have f of b minus f of a. So if we take some liberty here and we define the integral over a zero-dimensional region with just the points a and b, that we have, we call this interval I, this is the interval ab. Then we have the integral of f prime over the interval itself is equal to the integral over the boundary of the interval of f itself, and we define that to be f of b minus f of a. Now, an integral, of course, what you're doing is you're summing. But here we're taking f of b minus f of a, but that actually makes sense because here you can think of a one-dimensional normal vector. outward normal vector. So pointing outside of the interval in this direction, the normal is +1. Pointing outside of the interval in this direction, the normal is -1. So it's like we're taking the values of f at the endpoints, and we're taking a dot product with this normal vector, and we get f of b minus f of a, which is very similar to what's going on here. Here we're taking integral over surface of a vector field, dot product with the normal vector, and integrating over the surface. It's the same idea. Because here we have something that is 0-dimensional space, here we have a 2-dimensional space. So, the trouble is, we have all these theorems, 5 of them, that are very different in appearance. They all apply in very different situations. But in a way, they're all basically saying the same thing about this relationship of integrals over higher dimensional regions to lower dimensional. Here we have whatever function or vector field being integrated related to its derivatives in the higher dimensional integral. And it turns out that if we look at this the right way, if we use the right notation to describe what's going on, really all 5 of these theorems are saying exactly the same thing. So the point of differential forms is to introduce a new notation for describing entities that you're integrating over whatever region to be able to condense all 5 of these theorems into one. And the statement of the theorem is this. That if omega is a differential form and M is a k-dimensional manifold, and I won't get into what manifolds are in this class, but basically 1-dimensional is a curve, 2-dimensional is a surface, 3-dimensional it's a solid. Okay. And omega is a differential form defined in a region containing this manifold, that the integral of a form over a boundary is equal to the integral of a form's derivative over the interior. So all 5 of these are equivalent to this. We have one simple theorem that not only covers all of these cases, but in fact this statement and this notation can be used to cover more cases that these theorems don't. For instance, what if you have a vector field in a larger number of variables, 4-dimensional or more, and you're dealing with integration over higher dimensional objects? Well, generalizing these is going to be a problem because, for instance, a lot of these involve a cross product. A cross product is only defined 3 dimensions, no more, no less. You can scale it down to 2 for certain cases, like is done for Green's theorem. But the way we've defined everything, parameterizations of curves, surfaces, and all these different kinds of integrals, it really is limited to objects that we're familiar with: curves, surfaces, 2 dimensions, 3 dimensions. We're stuck in that world. But there is a need to be able to perform these kinds of tasks with any number of variables, and this notation won't let us do that. Differential forms will. So that's the point of this week, is to define what differential forms are, how to work with them, and then by re-examining all these theorems, we'll find that all of them are equivalent to this. So, in response to what I've heard from some students over the years that ask, isn't math done? Well, no, it's not, and well, hopefully never will be. Math is a notation, And if the notation that you have isn't serving your needs, you come up with something